Hi everyone, my name is Sabornawise Barry from Barry Science Lab, and today we're going to be talking about atoms. That's right. So we talked about the hydrogen atom last time. The hydrogen atom, well, not last time, but we've been talking about the hydrogen atom for a while now. But there's one important thing that I forgot to talk about. When we were talking about the hydrogen atom, we were only analyzing the motion of the electron. We were not talking about the proton. And furthermore, the hydrogen atom is not that interesting in the long run. Well, it is an interesting system for the fundamentals, but we're going to have to move on someday because a lot of the matter in this universe is not hydrogen, including most of the important matter. So, most matter is composed of atoms with a lot more electrons than just one. And here's the woeful part. Those electrons interact with each other. Now, here's the key example. Helium, this guy right over here, with 2 protons, 2 neutrons, and 2 electrons orbiting around it. Yes, you should know this model is extremely outdated by now. We can't do anything about it. Helium, right here, doesn't just have the interaction of the electron with the proton, which is what we've been discussing for so much time. Has these. But that's fine, right? In this case, all you have to do is, well, the equation that we have to solve is h phi is equal to E phi for some Hamiltonian h and for some energy level E. And if we were in the idealistic world where only these two reactions existed, what we could do is just write minus, what was it, h bar squared over 4 pi epsilon naught. Now I'm forgetting it. Let's say partial x r1 squared psi minus h bar, or e squared over 4 pi epsilon naught partial r2 squared psi is equal to e psi. Now, all you have to do is use separation of variables. Again, doesn't everybody love separation of variables? It's not really separation of variables, though, when you come to think of it. You just have the total solution is equal to the solution if there was only electron 1 multiplied by the solution if there was only electron 2. Wow, so that's interesting. Since the two electrons are functionally identical, we'll get to that in just a moment. Since the two electrons are identical, this is essentially just the hydrogen atom, but everything is multiplied by 2 squared. And so what that means is that ostensibly the minimum energy level is going to be multiplied by some power of 2. It's going to be multiplied by 8 according to our math here, right? But when we do this, we get minus 108.8 electron volts. So what went wrong? Well, here's the thing. There is a third relation. And of course, with that third relation comes a third term. And this term is the thing that's going to cause all of the problems in our life. So this term is the devil. And of course, once you add a third electron in another energy cell, we'll explain why there has to be multiple cells in just a moment. Once you add an electron outside that, things just become worse and worse and even worse. Because now, which on the floor, part of the floor itself is peeling off. You also have the interaction between these two and between these two. as well as the very benign interaction between the nucleus in this guy. So things just get worse and worse as you add more dynamics. And by the time you get to, I don't know, something like sodium, it's totally unanalyzable without an approximation. So how do we approach this? Well, today we're going to be talking about atoms and Eves. First things first, I said two electrons are functionally identical. Now this is the exact reason why, and you've probably been wondering for a while, atoms have shells. When one shell is filled up, you need another one. And when that shell is filled up, you need another. Yes, I know I drew 4 and there are actually 8. Please don't complain. I don't have the time to draw 8. So, what is the explanation behind this? Well, here's the thing. In classical mechanics, if we have objects A and B, even if I say they're functionally identical, they can be identified separately by two different things. Say one is red and one is blue, or one is left and one is right, or one is not a good circle while one is a good circle. Or, I mean, what else is there to say? There are so many different things that you can observe that makes A clearly different from B. There are no two classical objects that are perfectly identical. And if there are, you can still keep track of them because you know observation is not going to change anything about them. That does not apply to quantum mechanics. Now, let's say you have two electrons. Here's the problem. A, they're functionally identical. And B, well, what can you say about it? Maybe you can distinguish them by, I don't know, their spin or their position. Here's the problem. A, those things change on random. They're uncertain. Remember, we highlighted the uncertainty principle a while ago. And B, you don't know if an observation is going to spontaneously change in position. I mean, if when you had two identical objects, except one was colored red and one was colored blue in front of you, and you knew observing them might spontaneously change their color, you wouldn't be sure either of which is which, would you? So that means we have to treat everything like it's functionally identical. And what does that mean for us? Well, we have to display some wave function where it's symmetrical. That is, you can exchange x1 and x2 without any major events occurring. So for boson, you get psi plus, which is equal to psi a x1, psi b x2, minus psi a x2, psi b x1. Minus, you instead get, oh, why did I put a minus? Wrong. So when you switch the orders of x1 and x2 here, these two should stay the same. Why? Well, I mean, you can never know which one is in state psi 1 and which one is in state psi 2. You cannot say electron 1 is in state 1 and electron 2 is in state 2. They are the same. You can't identify them with numbers. Instead, all you can say is that one of them has got to be in psi 1 and one of them has got to be in psi 2. But you might preventing them from taking the same state. Well, here's the gist of it. The same electron with the same quantum number and the exact same spin cannot exist in the same place at the same time. Now, it's actually a very inaccurate metaphor, so let's make it a little bit more rigorous. Now, this only applies to fermions, the vast majority of matter in our universe, including protons, neutrons, and electrons, which are particles with half spin. Now, if you have half spin, you identify with this wave function. And if with this wave function, if you have that psi A, hold up, sorry, this should be psi bx1, psi ax2. I'm not sure how I messed that up. This should be psi bx1, psi ax2. Now, you should say that if psi A and psi B are the same, that is, the two particles are in the same state, then that's totally fine. For a boson, for a fermion, that means that, well, psi ax1, psi ax2 minus psi ax1, psi ax2, the wave function will collapse. And that's not good, because that means the particles never existed in the first place. Not just that, that's not normalizable. And normalizable wave functions, as we know, don't mean anything. Essentially, reality will collapse if two particles of the same type, which means they have the same charge and everything, the same mass, which means they have the same charge, the same mass, the same spin. Two particles of the same type with the same state and the same quantum number cannot exist at the same time. So, how does that answer the question of why there were two electrons in the first shell? All that means is that one electron will take one of the spins, and there are only two spins possible in this first state. So, the other electron has to take the other spin. And whoop-de-doo, there can't be any more electrons in this shell, because it would have to take one of the two spins, up or down. If it took the up spin, it would be in the exact same quantum state as this first electron. And that's not allowed. If it took the down spin, it would be in the same exact quantum state as the second electron, which is also not allowed. So that means the only way to remedy things is for this electron to actually change its quantum number. And the only way to do that is by raising your energy level. And that's why, in the Bohr model at least, it grows farther away from the nucleus. Now, the full details of that will be explained next lecture. Why the shells are 2, 8, 18, and so on. No, it is not just 2n squared, although that is the pattern they follow. So, now we know these things, right? But to continue forward, I think we need to bring back a little bit of a reminder of what quantum mechanics really tells us. Remember, quantum mechanics is unfortunately all about probability. And Einstein was a little bit wrong when he said God does not play dice. Because clearly, whatever created this universe does like gambling. But how? Well, just as a callback, we now have operators that can take on both eigenvalues, which is what we explored with the angular momentum operator, and they can take on expected values, which is a callback to the probabilistic nature of quantum mechanics. Quantum mechanics hinges on Born's statistical interpretation. you know this thing. So from a to b dx, and of course it's actually more like dr cubed or d cubed r. This thing is what tells us the probability of something happening from a to b of the particle that this wave function describes being found from a to b at any given time that we have to actually plug into the equation. This is quantum mechanics at its purest, and that means we can also assign an expected value to operators, mostly by just multiplying them by the wave function and seeing what happens. So we can actually define an expected value for any operator. And remember, when we're in the funky world of quantum mechanics, pretty much anything can be an operator. Momentum? Yeah, that's an operator. Position? Yeah, that also sounds like an operator to me too. Angular momentum? Yeah, that's an operator as well. Spin? Yep, also an operator. And of course, the state of any particle, which is just all of these combined. Can you take a guess what it's going to be? That's right, an operator. So, since everything in this universe is an operator, at this point, I might even be an operator. That means we can also assign expected values. So, we can now tinker around with things like this. Now, because we want to find how the forces between electrons affect each other according to Coulomb's law, here's the thing. Coulomb was stupid. No, he's not stupid. I'm just kidding. Coulomb assumed that you can actually know what R is for certain. You know absolutely what the magnitude of R is. And of course, that's not certain because these two electrons don't have a fixed distance between each other. We don't even know where they are. We only have a probabilistic sense of where they might be. And of course, having a probability distribution of where they might be allows us to, through a lot of, okay, good thing it didn't shatter, through a lot of probability theory, work out a probability distribution for what the distance between them could be. And of course, we need what the distance between them could be in order to figure out what to plug in to Coulomb's law. Yes, Coulomb's law is still haunting us 300 years later. Unfortunately. Fortunately or unfortunately. All right. So, as a callback, I'm only going to be using the negative sign because we do not discuss bosons in this household, which means we're only going to be taking the negative wave function, which is sine 1 x1, psi 2 x2, should be psi a, psi b, minus psi b x1, psi a x2. Now, when you have this thing in front of you, let's say you want to find the expected value of the distance between object A and object B. After all, that's what we need in order to apply Coulomb's law. So how do you do that? Well, if the particles are distinguishable, then that's easy. This is just, I'm going to abbreviate x2 minus x1 as x. This is just, that's not it. This is just x1 squared plus x2 squared minus to x1, x2. But here's the problem. Electrons, the way we're dealing with them, in the helium atom, these two are totally indistinguishable. They're not indistinguishable, but they're almost indistinguishable. The only thing that can tell them apart is their spin, and that can change anytime we observe them, which means they are practically indistinguishable. So we have to come up with something new. Some expected value expression that will satisfy the helium atom. And how do we do that? Well, do you want me to continue it now? All right. Let's try to get into the integration. So, remember that when we're taking the expected value of an operator like this, that basically means we're taking this integral. So, that means we're going to be seeing a bunch of integrals of this kind when, we try to expand this. Oh, why did I put the square outside? To the inside. Squaring, something this. Yeah, so expected values, especially in quantum mechanics, don't have a lot of the properties that we wish they would have. But that's a story for another time, because we're not in probability class. Probability is discontinued indefinitely. So let's expand this. What do we get? Well, for x2 minus x1 squared in specific, well, you get x2 minus, well, what did you expect, man? Dx. And, of course, the big trick is that nothing commutes anymore because we're all sad. So these are operators now. And so squaring them has a pretty bizarre effect, right? Because you were essentially applying x2 minus x1 to x2 phi minus x1 phi. Which means that you now have x2 squared phi, minus, well, x1 phi minus x1 x2 phi plus x1 squared psi. And this whole thing is just telling us that when we factor it out, we get x2 hat squared minus x2 hat x1 hat minus x1 hat x2 hat plus x1 hat squared psi dx. And of course, this is equal to the integral of x2 minus x1 squared psi, which means that, naturally, this is the expected value of, since the expected value operator is linear, we can separate these out and say x2 squared minus x2 x1 minus x1 x2 plus x1 squared. Now, actually calculating these for the helium atom is an ordeal for another time, mostly because I don't have the work noted down. So, for now, that's it for today. Thank you everyone for watching, and we'll see you in the next one.